So question number 1, limit x tending to 2 and x squared minus 4 over x squared plus 4. So we can directly put the value of 2 in place of x because we can see that the denominator is not getting undefined for sure. So putting x as 2 in the denominator, we get 4 plus 4 is 8. In the numerator, 4 minus 4 is 0. So the limit is 0. Okay. A2, limit x tending to infinity, 4 minus x squared over x squared minus 1. Okay. If I put infinity in place of x, we get negative infinity over infinity. This is not a determinate form. This is not how we'll be able to determine the limits. So we'll have to do some simplification. Now, there are 2 or 3 basic rules when it comes to rational expressions of this kind. This is not a simple polynomial expression. It's a rational expression. Has polynomials both in the numerator and denominator. In this case, we look at the degrees of the polynomials in the numerator and denominator. The degrees are same here in this case. So if the degree in the numerator is greater than the degree in the denominator, it's going to be infinity. If the degree in the denominator is greater than the degree in numerator, it's going to be a 0. Now when they're same, it's going to be a specific value, whole number value. So let's do one thing. We divide the numerator and denominator with x squared. So we get 4 over x squared minus 1 upon 1 minus 1 over x squared. Now you can put x as infinity. 4 over infinity becomes a 0. So this thing becomes a 0. 1 over x squared, this 1 over infinity will become a 0 again. So you are left with a negative 1 over 1, which is a negative 1. That's the answer. Okay. A3, limit x tending to 3, x minus 3 over x squared minus 2x minus 3. Let's check by putting a 3 directly first. So here 3 squared is 9 minus 2 times 3 is 6 minus 3. Okay, denominator is going to 0. We need to simplify because this will become undefined. So let's factorize. It's a clear hint that x minus 3 would get cancelled. Looks like that. So let's try the denominator, factorizing the denominator. It's negative 2x. So negative 3 positive 1. So 3 and negative 1. X minus 3, x plus 1, x minus 3 in the top. This and this cancelled. 1 upon x plus 1, x is 3. 1 upon 4. Option C is correct. Okay. Let's move on to the next page. Okay, A4. Limit x over x when x tends to 0. Okay. The expression is x over x. So basically the expression is, it looks independent of x. Okay. But if we would be placing x as 0 on the bottom, it won't be possible. Like, it'll turn the expression into an undefined one. Okay. So let's see how to do this one. For all non-zero x, x over x will be equal to 1, except for just one point where x is equal to 0. So if you look at it, it's going to look like, the function is going to look like, if we look at the graph. Okay. So if I draw the graph here for x is equal to 1, so basically y is equal to 1, it's simply 1 throughout, except for when x is equal to 0. That's a point of discontinuity. And then again, it's going to be 1 throughout. So the limit exists, although the function, this function would be discontinuous at x is equal to 0. But limit exists, because what does limit mean? Limit does not mean x is equal to 0. Limit means x is approaching 0. So it's approaching 0 from the left hand side, it's 1 still. From the right hand side, it's 1. So the limit exists. Left hand and right hand, they both exist. At x is equal to 0, it's not a defined function. Okay. So the value is a. The limit is a. Okay. If I have limit of x tending to 2, x cubed minus 8 over x squared minus 4. If I put 2 in the denominator and the numerator, I get a 0 over 0 form. This form is again an indeterminate form. Okay. So let's simplify. X cubed minus 8. A cubed minus b cubed. So x minus 2, because 8 is 2 cubed. X squared plus 4 plus 2x over x squared minus 4, x minus 2, x plus 2. This and this cancelled. Now put 2. 2 squared is 4. 2 times 2 is 4. 4 times 3 is 12 over 2 plus 2, 4. This is a 3. Answer is 3. Okay. A6. Limit x tending to infinity, 4 minus x squared over 4x squared minus x minus 2. Let's see how to do this one. We've done a similar question before. So as soon as you see x tending to infinity, and it's a rational expression, just check the degree of the polynomial on both numerator and denominator. In the numerator, the degree of polynomial is 2. In the denominator, it's also 2. So this is going to give us a whole number value, like a real value, not whole number necessary, but a real value. Okay. So 4 minus x squared, I divide the numerator and denominator with the highest degree of x, that is x squared. So 4 over x squared minus 1 over 4 minus 1 over x minus 2 over x squared. Okay, now put x is equal to infinity. So what happens? 4 over x squared goes to 0. 1 over x goes to 0. 2 over x squared goes to 0. Negative 1 over 4. That's the answer. Option B. A7. Limit x tending to negative infinity. 5x cubed plus 27 over 20x squared plus 10x plus 9. Okay. So let's see this one, how to do this. We will divide with the highest power of x, with the highest power of x. But before that, we need to check the degree of the polynomials. The numerator has a higher degree polynomial than the denominator. So in any case, whatever we try to do, there is going to be an infinity left in the numerator. Okay. So this is going to be a negative infinity thing. Why not positive infinity? Because x cubed, that's an odd power. Odd power of negative infinity will still give you negative infinity. So A7 is A. Okay. A8. Limit x tending to infinity. 3x squared plus 27 over x cubed minus 27. Okay. Now there are, again, this is a rational expression with a polynomial in the numerator and a polynomial in the denominator. Okay. So, and x is tending to infinity, so we'll check the degrees. The numerator has a lower degree polynomial compared to the denominator. That means there would be an infinity left in the denominator for sure. And if the denominator is infinite, the expression automatically becomes 0. The expression starts tending to 0, the limit. So let's see the options. We haven't seen the options yet for this question. So we have a 0 here in the options, and that is the correct answer, because the degree of the polynomial in the denominator is greater and it's going to infinity. Okay. A9. Limit x tending to infinity, 2 raised power negative x over 2 raised power x. Okay. 2 raised to the power of negative x over 2 raised to the power of x. Let's simplify this expression. 2 raised power, using the exponent rules, this would become negative x minus x, or 2 raised power negative 2x. This is the expression now. Let's quickly draw the graph. 2 raised power x is going to be this. 2 raised power negative x is going to be this. 2 raised power negative 2x will just be steeper, like this. Okay. Now x tending to infinity, they're asking. It's approaching 0. Option C. Okay. It could also be seen without the graph. How? 2 raised power negative 2x. This can also be written as 1 upon 2 raised power 2x. Remember the exponent rules. Now put x as infinity. 2 raised power infinity is going to be infinity, but 1 upon infinity is approaching 0. So option C is correct. A10. Limit x tends to negative infinity, 2 raised power negative x upon 2 raised power x. The same question, we have the graph in front of us. Yeah. It was asking initially for infinity, now it's negative infinity. At negative infinity, the value is infinity. See this one. So option D. Okay. Now limit sine of 5x over x when x is tending to 0. Okay. So sine of 5x over x. What I can write, we know sine of x over x if I was asked limit of sine of x over x tending to 0, this would be 1. Why? Because for very small values of angle x, the sine x is approximately equal to x. So x over x would become 1. So to make a similar expression here, in our case, we'll multiply and divide with a 5. I multiply with a 5, so I write a 5 outside. Limit x tends to 0, sine of 5x over 5x. Now limit sine of 5x over 5x is a 1. So 5 times 1, the value is 5. Limit is 5. Okay. Limit x tending to 0, sine of 2x over 3x. We do a similar approach. Multiply and divide with 2. So 2 limit x tending to 0, sine 2x over 2x, and leave the 3 outside. This 3 can be taken outside. It can be split. A constant value can be taken outside, although it cannot be taken outside from the 2x because 2x is going as an input to the function sine. Okay. Now sine 2x over 2x is a 1. So the answer is 2 over 3. Simply 2 over 3. Okay. Let's turn the page. Okay, A13. The graph of y is equal to arc tan x, which is y is equal to tan inverse x. Okay. So y is equal to tan x. Just remember the graph of y is equal to tan x. It's simply going from negative infinity to positive infinity between minus pi by 2 to pi by 2. This would simply translate, like rotate at 90 degrees towards the right or in the clockwise direction. It will become the graph of y is equal to tan inverse x. Or simply, it's also called taking mirror image about y is equal to x line. So the vertical asymptotes, would there be any vertical asymptotes? Since there are vertical asymptotes in the tan x graph, they would turn into horizontal asymptotes in the tan inverse x graph. So no vertical asymptotes in tan inverse. Option A is wrong. Horizontal asymptotes at x is equal to plus minus, y is equal to plus minus pi by 2. This is correct. Yes. This would become the y-axis. So let's quickly draw the graph of tan inverse x. This is the graph of tan inverse x. This is positive pi by 2. This is negative pi by 2. So you can see the asymptotes. Okay. A14. The graph of y is equal to x squared minus 9 over 3x minus 9 has. And there are a few options. We need to check the asymptotes, points of discontinuity, and these things. Let's quickly see that. Okay. So x squared minus 9 over 3x minus 9. This can be written as x minus 3 times x plus 3 on the top. And on the bottom 3 common x minus 3. Okay. Now, as we can see, just for x is equal to 3, the denominator goes to 0 and the function goes to infinity. Rest for all other values of x, the function is simply y is equal to x plus 3 over 3. It's simply this function. Okay. Just for that one point, x is equal to 3, it's going to a discontinuous value. Okay. So there is no asymptote. Asymptote means it's smoothly approaching that value. There's no smooth approach there. Okay. So as we can see, y is equal to x plus 3 over 3 would look somewhat like this. This would be the graph. It's basically y is equal to x over 3 plus 1. Okay. So y is equal to x over 3, 1 unit up. Now at x is equal to 3, what happens? This point goes hollow and it goes to infinity. Okay. So it's a point of discontinuity, but it's not a jump discontinuity. Okay. It's not a jump. It's like the function again continues from the same point. It had been a jump discontinuity if this function stayed in this straight line manner till x is equal to 3, and then it changed its path from there. Okay. So this is just a point discontinuity. Okay. It's not a jump one, and it's removable if we redefine the function as f of x is equal to what should we say at x is equal to 3 plus 3 is 6 over 3, 2. Okay. So at x is equal to 3, this is 2. So f of x should be equal to 2 at x is equal to 3. If we redefine the function like this, it becomes a removable discontinuity. So this is the answer. It's a removable discontinuity at x is equal to 4. Anytime you encounter a point discontinuity, it's removable. Okay? Because you can simply redefine the function at that point. Only jump discontinuities are non-removable. Okay. So this is the answer. A15, limit x tending to 0 sine of x over x squared plus 3x. Okay, x squared plus 3x is again going to give us 0 in the denominator. So we cannot do that. So what we can do is limit sine of x over x times x plus 3. Okay. Now we can treat these as two different functions. How? We can split this as sine of x over x as 1 multiplied by 1 upon x plus 3. Okay. And then we take the limit. So the limit would be done separately for these two parts of the function. Limit of sine x over x is simply a 1 times limit of 1 over x plus 3, where x is 0, is 1 by 3. Option B is correct. Okay. Next question. Limit x tends to 0 sine of 1 over x is x is tending to 0, 1 over x would be tending to infinity. Sine of infinity is going to be what? Let's see. So if I look at this curve, the sine curve, it keeps on going. So at infinity, it would still show the same nature which it's showing for any other values. Okay, so let's see how to do this one. We took a look at the sine curve. Okay, and by nature, sine function is an oscillating function. It takes on different values ranging between -1 and 1. Okay, so as we saw, x tends to 0, 1 over x tends to infinity. That means it'll take on a varying range of very large values. Okay, that's what 1 over x would do. Okay, so at that infinite range, the sine function would still be oscillating. So the limit exactly cannot be determined because the function itself is an oscillatory one. So this is also called an oscillating discontinuity. So the function sine of 1 over x would exhibit an oscillating discontinuity at x is equal to 0, or when the input is going to infinite. So the limit is non-existent. Limit does not exist for sine of 1 over x for x tending to 0. Okay, let's go to the next one. A17, which statement is true about the curve y is equal to 2x squared plus 4 over 2 plus 7x minus 4x squared? And looking at the options, it's all about asymptotes. That means we need to check the denominator. Okay, so 2 plus 7x minus 4x squared, negative sign taken outside, 4x squared minus 7x minus 2. Let's factorize this. This becomes 4x squared minus 8x plus x minus 2, and that becomes 4x x minus 2 plus 1 x minus 2. So x is equal to -1 over 4 and x is equal to 2. These two are the roots of the denominator. That's where the denominator becomes 0. Okay. The numerator, being the numerator, it's always positive. This expression 2x squared plus 4 will always be positive. Okay. Now, when does the vertical asymptote occur? Let's see. Vertical asymptote occurs when the denominator becomes 0 or the function goes to infinity. Okay. The value of x where the function goes to infinity. That's the vertical asymptote. What is the horizontal asymptote? The value which y approaches as x tends to infinity. Okay. So if we want to check for what happens when x tends to infinity, let's quickly solve the limit for x tending to infinity for this one. So divide the numerator and denominator by x squared. We get 2 plus 4 over x squared over 2 over x squared plus 7 over x minus 4. Now put x as infinity. What happens? This goes to 0, this goes to 0, this goes to 0. Okay, 2 over -4. That's -1 over 2. That's what it is. Okay, so 2 over -4. That's -1 over 2. This is the value which y will be approaching when x tends to infinity. So the horizontal asymptote is going to be -1 over 2. So horizontal asymptote options are wrong. The vertical asymptote is going to be at x is equal to -1 over 4 and x is equal to 2. So this is also wrong. Option A is correct. Okay. Question number 18. Limit x tending to infinity 2x squared plus 1 over 2 minus x 2 plus x. Okay, let's see. X is tending to infinity. The degree of the polynomial is same in the numerator and denominator both. 2x squared plus 1 over 2 minus x, 2 plus x is 4 minus x squared. Now what do? Divide with x squared on top and bottom. So you get 2 plus 1 by x squared over 4 by x squared minus 1. This and this cancelled. Negative 2 is the answer. Question number 19. Limit x tending to 0 mod of x over x is. Okay. Mod of x over x tending to 0. For the value, so this would, to check the limit for this, since it's a mod of x, it is different for x less than 0 and x greater than 0. We'll have to check the left hand limit and the right hand limit to see if the limit exists. Okay. So for x tending to 0 minus, that means it's approaching from the left side, slightly less than 0 values. This mod of x would become a negative x over the x will remain x. So this becomes a negative 1. Okay. For 0 minus, it's a negative 1. For x tending to 0 plus, that is slightly greater than 0. It's coming from the right. Mod of x would be x over x, which is 1. So left hand limit is minus 1, right hand limit is plus 1, not existent. The limit does not exist. Okay. 20. Limit x tends to infinity, x sine of 1 over x. Okay. So x sine of 1 over x. This x inside, if I turn it to infinity, 1 over infinity will become 0. And sine of 0 is 0, approximately 0. But this x here is infinite, and infinity times 0 is indeterminate. So let's see how to do this one. Okay. Okay, there are multiple ways to do this, but I'll tell you the most intuitive one for this one. Okay. So x sine 1 over x when x tends to infinity. If you look at the sine curve, for very small values of angle, we can say, like let's say sine of x is approximately equal to x for very small x less than 0 or 1, like that. Okay. For very small values of x or angle, the sine of the angle is approximately equal to the angle itself. Going by that rule, you can say x times 1 over x, because 1 over x is really, really small in terms of the angle value. So this becomes a 1 directly. Okay. It'll become a 1. That's one way to do it. The other way to do it is the way you've done the previous questions of sine x over x. So we know limit of x tending to 0 sine x over x. This is 1, which is the same as saying limit of x tending to infinity sine of 1 over x over 1 over x. This is also equal to 1. Why? Because when x tends to infinity, 1 over x and 1 over x, they will also go to 0. So the expression is similar to this one. Hence, the limit of this function is 1. Okay. Let's go to the next one. Limit x tending to pi sine of pi minus x over pi minus x. Okay, really very simple. They haven't done much. They've just changed x to pi from x to 0. But this expression, pi minus x, would tend to 0 at x tending to pi. So this is simply like limit x tends to 0 sine of x over x, which is equal to 1. So that's your answer. Okay. 22. Let f of x is equal to x squared minus 1 over x minus 1 for x not equal to 1, and 4 for x equal to 1. Okay. So for x not equal to 1, if we simplify this, the first one, it's x minus 1, x plus 1 over x minus 1. So simply x plus 1. This is for x not equal to 1. And for x equal to 1, it's 4. Which of the following statements is or are true? Okay. Limit x tending to 1 f of x exists. Okay. If we check for x tending to 1, the limit left hand side and right hand side, Left hand side, let's say 1 minus, this is going to be 2, 1 plus, again it's going to be 2. It exists. Yep, this is correct. F of 1 exists. F of 1, yeah, does exist. The f of 1 value is 4. It's a whole number value. Yep. F is continuous at x equal to 1? Wrong. It's discontinuous. And what kind of a discontinuity is it? It's a removable point discontinuity. Okay. So the function is going like x plus 1 just at x is equal to 4. It's a hollow point and it's some 4 instead of being a 2 here. So it's a removable discontinuity. 1 and 2 are correct. Okay. A23. If f of x is equal to x square minus x over 2x for x not equal to 0 and f of 0 is k, and if f is continuous at x is equal to 0, then k is. Okay, perfect. For f to be continuous at x is equal to 0, k should be the same value which occurs at this function at x is equal to 0. Let's see. So x, I take common on the numerator, x minus 1 over 2x. X and x cancelled, x minus 1 over 2. Okay, x minus 1 over 2, and if we check the limit now, left hand limit 0 minus, so 0 minus 1, this is going to be negative 1/2, and right hand limit, this would be 0 positive, again negative 1/2. So k is basically negative 1/2 if this function has to be continuous. Option B, which is negative 1/2. Okay. So we've done 23 questions from here. I am stopping this video here for you to practice properly these questions and you get the concepts correct. The next video is going to have more complex questions, more difficult questions. Okay, and it will have the calculator section as well. So stay tuned for part 2 of the limits and discontinuities, or limits and continuities. Okay, and stay subscribed, keep watching this space, and let me know in the comments which other videos you need. Okay, thank you.